Bismillah ar-Rahman Rahim. My name is Dr. Afaq Ahmed, and I'm working as an associate professor at Center of Excellence in Solid-State Physics, University of the Punjab. The topic of my two-day talk is electron affinity for hydrogen negative ion in photodetachment microscopy. In this talk, I shall briefly explain the theoretical imaging method first and then apply it to the hydrogen negative ion to investigate the electron affinity with the help of the well-known Einstein photoelectric effect. In result sections, I will explain the two things. One is electron flux and other is the neutron rings. In conclusions, the electron affinity of hydrogen negative ion that will be 0.75 per electron volt. Uh, First of all, I would like to explain the electron affinity. Electron affinity actually is a very important parameter which explains the binding force in between the extra electron with the neutral atoms and molecules. Um, this is an important parameter that defines how the extra electron that attach with the neutral atom are molecules. Now we'll discuss a little bit about the theoretical imaging method. In this method, this figure explains O is a position of the hydrogen negative ion, and it placed near the near any wall, reflecting wall. The distance between the hydrogen negative ion and the wall is d, and the distance between the hydrogen negative ion with the observation plane is capital L. In this theoretical imaging method, I'm taking the two outgoing detached electron waves after the photodetachment process. One is moving directly towards the observation plane, which is defined by the side direct, and another after reflection from the wall it reaches to the observation plane, and this is represented by the psi returning. When these two waves reaches at the observation plane, we will get the interference pattern, which is look like as a uh, Newton rings. Um, so how we will get the mathematical steps for this process? The mathematical step, the direct outgoing wave is represented by the this expressions, where C is a constant. C is a constant that is given by the 4k bi over kb square plus k square whole square, and exponential iota k r1 or r1, where k is actually related with the detached electron energy in this expressions, and kb that is related with the binding energy or the electron affinity of the hydrogen negative ion, and p here is the normalization constant. The second returning wave, it can very easily deduce from the outgoing detached electron wave just by incorporating the phase difference in these expressions. That is a mu pi by 2, where mu is a Maslow index, mu that defines the nature of the wall. When mu is equal to 1, the wall is look like as a soft wall. Mu is equal to 2, the wall is a hard wall. Um, in this equation, when these two waves reach to the observation plane, they superimpose to each other. We will get the final wave. That is a psi is equal to psi direct plus psi returning. After getting this final wave, we put this final wave into the formula number 3 that defines the electron flux in terms of the total wave functions. When I put this wave functions into these expressions, we will get the electron flux on the screen, and particularly the electron flux on the screen in the so when we put this total wave function into the equation number 3 with the as well using the large distance approximations, that is r1 is equal to r minus d cos theta and r2 is equal to r plus d cos theta, and for other places we are using this kind of the approximations, then finally we will get the electron flux along the z directions, z directions that is given by in these expressions. J0 is equal to 2k. C absolute square L square over O square plus L square whole power pi by 2, 1 minus sine 2k dl over O square L square. This expression's final expression clearly shows that the electron density is a sinusoidal function that has an oscillatory behavior. It contains some ripples. As we increase the value of k that depend upon the photon energy, the number of peaks in this expression also increases. um, in this expression, c is the same as we have already defined, and k is a relation related as 2 e is equal to e photon minus eb, that is a detached electron energy. So this expression also shows that for any peak value, this sine function vanishes. That is, when I put the 2 n pi is equal to 2 k dl over O square L square, this sine function vanishes here. We say that there is an n number of peaks in this expression, then the 2 n pi is equal to 2 k dl over O square L square. Uh, Therefore, by simplifying this, n is equal to kdl over pi or square L square square root. Let we take the dl over pi rho square L square square root is equal to a is a constant factor, so we can write it as n equal to a 2 e photon minus e pi, e pi, and n square is equal to a square. By taking the square on both sides, we'll get the n square is equal to a square 2 e photon minus e b. Our n square is equal to 2a square e photon minus 2a square b. By examining these equations, we can say that this is a straight line equation in terms of n square and e photon. When someone makes an relations in makes a graph in between the n square and e photon, we will always get a straight line. So this equation 5 concluded that the number of peaks in the electron flux and the photon energy has a linear relationship, and this linear relationship guide us and finally give us the electron affinity of the negative ion. So plotting the electron flux versus the rho, we obtain this kind of the behavior. For 1 electron volt, we are seeing that the number of peaks in the electron flux are these are the three, 1, 2, and 3. There is a 3 number of peaks. While as we increase the energy, the number of peaks are also increases. It will become as a 6 here. And for 3 electron volt, the number of peaks increases and it becomes 8. And for 4 electron volt, the number of peaks increases to 10. The corresponding Newton rings for this electron flux is given by in this graph. Similarly, you can see that for 1 electron volt, the number of rings 1, 2, and 1, 2, and 3. Third rings are not clearly visible, but there are 3 number of rings in this way. And similarly, as we increase the energy 2 electron volt, the number of rings becomes 1, 2, 3, 4, and 5, and 6 up to so on. And similarly, for when you increase the energy, the number of rings becomes 8. And for 4 electron volt, the number of rings increases. So by increasing the photon energy, the number of rings also increases. We finally makes a table that's for 1 electron volt, the number of rings is 3, 2 electron volt, 6, 8, and 10 respectively. So finally, we make a graph in between n square and e photon. Our theory says that the graph in between n square and e photon must be a straight line. So after getting the graph, that would look like as a straight line in between the n equal 1 electron volt. This is the neutron rings here, and 2 electron volt, the neutron rings here, and 3 electron volt and 4 electron volts. That's a corresponding number of peaks n square versus So by extrapolating this graph to the lower value of the photon energy, we will get the threshold value that is equal to 0.754 electron volt, and this value is known as electron affinity. In conclusions, we can say that the electron affinity of hydrogen negative ion is determined using the theoretical imaging method along with the well-known photoelectric effect. And the theoretical imaging method is actually was actually basically formulated for the determination of the total and differential cross sections near any plane. It is very simple and straightforward method. We suggest experimentalists that the electron affinity of the negative ion can be found by inspecting circular interference pattern for the different photon energies similar to the procedure provided in this research. Uh, so this is our theoretical group at working at Center of Excellence in Solid State Physics. Thank you.